Should be continuing along in lab. You have the outline. You should have a game plan when you come to lab. Let me know if you have any questions. Okay, acid derivatives. I think this is the white handout. We need to go back and look at this material. I actually jumped ahead a little bit on last Wednesday. A little bit of introductory material here. It's sort of very general. It should make sense. Okay, nucleophilic acyl substitution. Yeah, that's what we're doing. I have a carbonyl group with some type of leaving group, and we can replace the leaving group with a nucleophile. All right, it's a substitution reaction. X being leaving group here. I'm not showing any charges. May or may not be charged. This is not SN1 or SN2, obviously, because this is not a tetrahedral carbon, but rather this is an addition-elimination mechanism. A lot like NAS for aromatic substitution, this is acyl substitution. Nucleophile adds to carbonyl. Which bond are we going to break? Sigma bond to leaving group or pi bond to oxygen? Pi bond to oxygen, so electrons up is what I'll say. We get this tetrahedral intermediate because the carbonyl carbon is now tetrahedral. Addition, nucleophilic addition. Now we can eliminate, the electrons can come back down and we can then kick off the leaving group in a fast step, reforming the neutral carbonyl. Because it's a fast step, we do not have strict leaving group requirements here like we do for SN1 or SN2, in which the leaving group leaves in the slow step, rate determining hard step. General addition-elimination mechanism. Note that this general mechanism does not include acid catalyst here. If we have an acid catalyst, there's going to be additional steps along the way as we take care of the proton. All right. For example, we may do a proton transfer at this point before we eliminate. So that's just a simplistic two-step process there. Reaction coordinate diagram, yeah. First step is rate determining. Second step is fast. Should make sense, yeah? Discussion of leaving groups. Lots of things can leave carbonyls. Oxygen, nitrogen, sulfur, even carbon. If the carbon is stabilized somehow, such as when we look at the haloform reaction. You are not going to eliminate a standard like methyl alkyl group or hydrogen. Okay? X can be a variety of things. It's not going to be a plain carbon group or hydrogen. But if you've ever seen it be minus before, it can leave in this type of mechanism in a fast step. Please read here. I'm not going to read every little thing to you here. Reactivity of acid derivatives. Okay, we need to know our acid derivatives. We need to know nomenclature. That's video. Reactivity of acid derivatives towards what? Towards NAS, nucleophilic acyl substitution. Acid chlorides are most reactive, followed by this is anhydride. Oxygen bonding to two carbonyls. And anhydride. And that's more reactive than esters. And esters are more reactive than amides. Amides are your least reactive. NAS. Of course, that was shown back over here in the table or the diagram. Derivatives shown in order of increasing reactivity. Acid chlorides, then anhydrides, then esters, then amides. Okay, I'm not including nitriles in the current listing. Why are acid chlorides the most reactive? Well, first of all these carbonyl derivatives have the carbonyl, okay? There's the dipole. The dipole's there. Dipole is there. But everyone has that, so there's no use talking about that. That's consistent. The difference is, well, this has chlorine. Others have oxygen. The chlorine has a bigger dipole. It's more electronegative. And so because of this, there's more partial plus here. That's a very electrophilic carbon. Very electron poor. Lots of partial plus character there. Nucleophiles are going to be attracted there and react there. Nucleophilic addition. All right? Anhydride is oxygen. Oxygen is bonded here. Now there are two carbonyls. We'll look at anhydrides. When you deal with anhydrides, only one carbonyl is reacting, really. Let's look at ester first. It can be easier to compare acid chloride to ester. Okay? Oxygen is more electronegative than carbon, so it does pull inductively, but it can also donate by resonance. Chlorine can too. It can pull inductively, but it can also donate by resonance. Which is the net major effect for oxygen? It's the same as with aromatics. Resonance is a stronger effect with oxygen. And so the donation is greater with oxygen. So any partial plus that might be here from withdrawing is sort of quenched by the donation. What's the net effect with chlorine? It's the same as with aromatics. When it can do both. Because chlorine can pull inductively. Chlorine can also donate by resonance. It has a lone pair. What's the net effect with chlorine? Induction, just like with aromatics. Okay? Chlorine's a net withdrawer. Net withdrawer. And that's actually a net donator. So this carbon should be less electrophilic with oxygen. We'll compare the ester to the anhydride. Which oxygen can donate more towards the carbonyl? This one or this one? Again, there's two here. Let's just consider this side. How much can this oxygen donate to that carbonyl? More or less than that? Less, because that oxygen is at the same time doing what? It's donating the other way. And since it's donating the other way, it can't donate this way as much. So that's why the anhydride is more reactive than the ester. Again, just one side. When we do anhydride chemistry, all that will be the leaving group. We just look at one carbonyl, all the rest is the leaving group off of that carbonyl. The least reactive is the amides. Yes, this can withdraw, but the nitrogen donates. Which donates more, nitrogen lone pair or oxygen lone pair? Nitrogen. Nitrogen, why? More what? More likely to be plus or more willing to be plus. Oxygen is more electronegative. Does oxygen like becoming plus? No, it doesn't love it, but it will do it as long as it has an octet. Nitrogen doesn't mind being plus as much. Nitrogen doesn't mind being plus. Nitrogen is a strong donator by resonance. Thus, how much partial positive do you really have here? Why would you have any? Because of the carbonyl. But again, all carbonyl derivatives have that. The lone pair quenches that partial plus by donating towards it. Now we're not going to show carbon with 5 bonds, but we can show the donation this way into the carbonyl. All right, you need to kind of get your thinking right here. The donation of the nitrogen in an amide is very significant. That's why amides are the least reactive towards nucleophiles. Significant contribution. And we can do resonance structure. We can show that contribution. Significant contribution for such a resonance structure. Nitrogen really likes to donate by resonance. Look at this compound. This is called DMF. I discussed it on the nomenclature video. How many are these methyls equivalent in NMR or not? Are those methyls? How many signals would you expect for the methyls in the NMR or DMF?
2.
Why 2? How many signals for the methyls? How many signals for the methyls?
2. 2, because of the restriction on that one.
Okay. How about this compound? How many signals for the 2 methyls? Methyl on here and here.
Just 1.
1 signal, yeah? Okay. Well, change that to nitrogen. How many signals for the methyls? Still 1. That's what you should think initially. It's not 1. It's actually 2. The reason it's 2 signals is because, well, why would this be 1? Why would you think 1?
Rotation.
Because free rotation, this can just rotate. This methyl is here, this methyl is here. Free rotation, now whether it's nitrogen or carbon, that's why we got symmetry. Okay? In DMF, you actually get 2 signals for the methyls. Because such a large contribution for this resonance structure. Here, one methyl is cis to the oxygen, the other is trans. Can these rotate?
No.
Why can't they rotate?
Pi bond.
Because of the pi bond there.
Pi bond here. Can they rotate here?
Yes.
If the structure was just single bond, this should be able to rotate and these should be equivalent. But they're not. There's significant pi bond between here. That's what resonance means. What's the true structure? It's a blend. What's the bond order between the nitrogen and carbon here?
1.5.
1.5 if you just say, okay, but which one's major? This is probably major because of the charge, but that's very significant. There's a lot of pi bond in here. A lot of pi bond character, and that's going to restrict the rotation. Well, let's go to the NMR. NMR is on the next page of DMF. How many signals do we have for the methyls?
2.
2 signals. And then the H is kind of like an aldehyde. It's not an aldehyde, but it's kind of like an aldehyde. It's way downfield, about 8 or 9, yeah, from 9 to 10. Signal for water here. 2 methyls. Okay. This is experimental evidence for resonance. Okay? It's due to resonance. In the conjugation, lone pair conjugated with carbonyls restricts the rotation, makes the methyls non-equivalent. Yeah? Pretty good, yeah?
Mm-hmm.
You didn't know you were going to see NMR evidence for resonance this morning, did you? So, interconversion of acid derivatives. You can only convert to a less reactive derivative. Acid chlorides can be converted to anhydrides, esters, or amides because all 3 of those are less reactive. Esters can only be converted to what? What's less reactive than an ester?
Amide.
Only an amide. Now this is direct conversion, okay? I can convert an ester to an acid chloride, but it ain't going to be in a single direct conversion. It have to be multiple steps. And by the way, all acid derivatives can be converted to what?
Carboxylic acids.
Carboxylic acid. Yes. You are not going to directly convert an amide to an acid chloride by perhaps trying to react it with Cl-. Okay? Because you do not go from a less reactive to a more reactive derivative. Why is this? Well, the reactivity scale, leaving group ability, nucleophilic ability. Let's look at this. If we had an amide, and we tried to react it with Cl-, first off, amides are not that reactive, even though it's a carbonyl. Least reactive carbonyl. Worst nucleophile, Cl-. Even though it's an anion, yeah, it's just not a great nucleophile. And going the other way gives you a better nucleophile. Okay? In terms of nitrogen, oxygen, or that, it's the worst nucleophile. Also, so you just don't have good reactivity. But even if you could get this to react here and get you to a tetrahedral intermediate, when the electrons come back down, which leaving group is it going to kick off, the Cl or the nitrogen?
The Cl.
Chlorine's a better leaving group. So even if it does do an addition, it's just going to come back down and get kicked right back off. So this is why it just doesn't work. And you cannot convert a less reactive derivative to a more reactive derivative. Not directly. All right, so that's just not going to. Compare, on the other hand, if we had an acid chloride, we can convert it to an amide by reacting with ammonia. Well, we have a very reactive carbonyl, lots of partial plus because of the net withdrawing of the chlorine. Pretty good nucleophile. Even though it's neutral, amines are good nucleophiles. And so you got good reactivity here. You get to this point. Now I have lost an H. All right? We got to take care of protons. This is very generic. We have lost an H here. So to take care of the proton. But if we get to this point, what's a better leaving group, Cl or nitrogen?
Cl.
Cl. It's more electronegative. It's going to be able to be a minus better than nitrogen can be minus. And so everything sort of falls into place, and we can go from a more reactive to a less reactive derivative. Okay? General concept, and we talked about this on Wednesday. We included this in our mechanisms. And that's the idea of protonating the carbonyl. Protonation of the carbonyl makes it more reactive, more electrophilic. Very common step in a mechanism. For example, an ester will not react with water. No reaction. Water will not come in here and kick off the methanol. However, if we have water and an acid catalyst, which by the way combine to make H3O+, we can get a reaction. So the H+ will catalyze the reaction. And how it catalyzes it is the carbonyl oxygen reacts with the acid proton to get a protonated carbonyl, and the oxygen is now positive. Because the oxygen is positive, there's even more partial plus on this carbon because this oxygen pools. Which one pools more? Neutral oxygen or positive oxygen? Positive oxygen pools more. I'm mad. Hey, I don't like this. Give me electrons, carbon. Okay? And so that's more partial plus. More partial plus. We can illustrate this also by resonance. You can just take this and move the electrons up, and we can say, hey, there's lots of partial plus character here. If you want, you can even work with this resonance structure. And so the nucleophile is more likely to add to a protonated carbonyl than to a neutral carbonyl. Protonation of the carbonyl makes the carbonyl more electrophilic, more reactive towards nucleophiles.
Would it never protonate the methanol?
You could. You could. It's an important question because if you've got acid around, you're going to be protonating anything that's protonatable. Okay? It's kind of like, you know, you throw all your clothes in the laundry and you say, hey, your socks are going to get wet. Then you're like, is my t-shirt going to get wet? Yes, it's going to get wet too. What about my blue jeans? Yes, I just focused on the socks, but everything's going to get wet. It's an important question. We can't forget.
Because that would decrease the reactivity of it. I mean, increase it, I'm sorry.
I didn't hear.
It would affect the reactivity of it,
Of the what?
of the carbonyl.
But you got to consider equilibrium though. Now, How strong of a base is this? Is that a strong base? What's a strong base? Anions or sp3 nitrogen. Not a strong base, no. Where did we just protonate something at? Right here. Right here. Let's okay. This is just an acid-base reaction. Everybody agree? So what's the pKa's? We can consider this by pKa. A pKa of a strong acid is like -5. The pK of this is probably -4. I don't like this. I'd rather not do that because then the numbers don't really help explain it. The numbers make it look even more confusing. Here we go. Let's look at this. Which side do you think is favored? Actually, this side is favored. This is tough because if I tell you the truth, it's going to be confusing. Here it is. This is what I think the truth is. This side is favored. The equilibrium is really this. Let's look at it like this, okay? When we protonate carbonyl, how much do we protonate? How many of the carbonyls are protonated out of 1,000,000? Not many. Not many. 1 out of 1,000,000. But guess what? That one that's protonated is the one that's going to react. And when it reacts, it's gone. What happens to the equilibrium of 1 in 1,000,000? Another one becomes protonated. Then it reacts. Then another one gets protonated. At any given time, the carbonyl is probably not protonated much. It ain't basic. All right? And that's a very important point. It's not a strong base. I mean, organic 1, we never would have protonated it. We would have considered it neutral, non-basic. Okay? Only protonate very little bit at a time. But that protonation is very important. That 1 out of 1,000,000 is very important. Okay. That includes protonated carbonyl, also includes aldehydes and ketones. Test 4. Any carbonyl, protonation. When you get to biochem, you'll just see protonated carbonyls. It'll be like, where'd the proton come from? It'll be like, well, it's protonated. All right? The time for questions is now. Okay, that's some background, general stuff there. Okay, let's get back to mechanisms. And there's some other good stuff there. Mechanisms. We ended with the Fischer esterification. Fischer esterification. Converting a carboxylic acid to an ester. Reacting with an alcohol. And a what? An H+ catalyst. What was the first step of this mechanism? Protonate the carbonyl. Carbonyl chemistry, H+ catalyst. The first step you're always going to do is protonate carbonyl. Okay? All right, we looked at the mechanism. We had it all on the board. I wish we still had it. You got it on your paper. Here, this reaction is a true equilibrium reaction. Okay? Every step we did was reversible. We were doing that at the very end. All right? Every step is reversible. You do that, you go backwards every step. That is, the entire mechanism is reversible. How do you drive equilibrium? If you want to go from here to the ester, you got to drive the equilibrium. How would you drive it?
With your H plus catalyst?
Catalyst does not affect equilibrium.
Add more
This should have been that should have been discussed in Gen Chem.
Add more
Sound familiar? Catalysts do not adjust equilibrium, they only increase the rate at which equilibrium is obtained.
Add more carboxylic acid.
Okay, explain why would you do that? What's the rationale?
Le Chatelier.
Uh-huh. And he said what?
If you pump more product or reacting into a system, it'll shift to the products.
Okay. You can adjust equilibrium by
Adding more.
okay. You can add more acid, and you're saying if you add more acid, you'll get more.
Product.
Yeah, I agree. If you add more acid, you'll get more product.
Or you just remove the product and it'll.
Problem is, practically, your reaction ain't going to be. You'll never get done that way. Because you keep adding what you want to convert. And so practically, I don't know how that really works. Because practically what I want us to do is how can we convert all this to that? And if you think about it, adding more of this will create more of that, but you're always going to have more of that. You're never going to get rid of it by adding more of that, if you think about that.
Yeah.
What's another way we can drive this equilibrium?
Get rid of some of the ester?
Do it?
Get rid of some of the products.
You could. As this is formed, if you can somehow remove it from the flask, that will make, yeah, if we can remove this, then this will go more that way to replace that, right? That could be difficult. Here's another way to do it, is we can remove water as the water's formed. And that sometimes is easier. All right? If we remove water, then the equilibrium will adjust to create more water. And ultimately, all of it will go that way, and you'll be left with none here. Okay.
Are we removing water by refluxing or adding something to it to soak it up? Like if we were in lab, how would we remove it?
Actually, both. There are ways to actually remove water. It depends on the boiling point. Well, water's 100. Okay, what if we did that? Boiling point 100 degrees. We could do the reaction at, let's see if this will work. Do this at 120 degrees. Heat it at 120. As water is formed at 120, it's going to be boiling out. Problem is, what's the boiling point of your alcohol? Boiling point of ethanol is about 78. So if this was ethanol, could you do this?
No.
No, because the ethanol would boil out before the water did. That's sometimes a problem. Another way, yeah, you could use a drying agent, something that would soak up the water and effectively remove it from the equilibrium. That could be done. Molecular sieves. Even sodium sulfate could be used. Once the water adheres to the sodium sulfate, it's removed from the chemistry. Yeah. One of the most common ways to do this is to not add more acid, but add more alcohol, because this is your starting here. You got two starting, they're going there. Use excess. Excess, you know what excess is? Excess. A lot of times you just use excess alcohol. But only if the alcohol is easy to get rid of at the end. Like if it's a low boiling alcohol like methanol, ethanol. And very often that's how the Fischer esterification is done. You only use low boiling alcohols They're cheap and easy to get rid of. Because there's excess of this, the equilibrium is going to, when it's established, you're going to have a lot of this because there's so much more of the alcohol. Okay, has to be driven. On the other hand, we can do the reverse, and we'll talk about the reverse a little bit later, and I'll say, hey guys, it's just the reverse of a fissure. What is the reverse of a fissure? Ester going to what?
Carboxylic acids.
So hydrolysis. What is the ester reacting with to get to the acid?
Water.
Yes, these two react to go that way. It's a hydrolysis reacting with water. Okay, H plus catalyst. Water and H plus catalyst is what? H3O plus. And it's right here. What do you get if you react an ester with H3O plus?
Carboxylic acid.
Carboxylic acid, right? It's just the reverse of a fissure esterification. How would you reverse it? How would you make this go that way? And it's the exact opposite of every step we did in the mechanism. How would you make it go that way? You'd use lots of water. Lots of water and ester will drive it this way. All right? Just a reverse. I'm reminded to tell you this here. The more we go along in the remainder of the course, I think more and more it becomes important to organize your material. Okay? Organization. You know, there's really only one mechanism for test 3. It's called nucleophilic acyl substitution. Problem is the little variations in it. And the little variations, I just mentioning them, you won't even recognize them. You have got to organize and see all the chemistry that's going on. All right, organization, see what we have. What are we doing? Another way to make esters from carboxylic acids. We can do the old-fashioned way, which we probably saw in Organic 1 by an SN2. If we take an acid and treat it with some type of base, what can we get here? What's acidic? We can get the carboxylate anion. What base would you suggest could do this? NaOH? Yeah. We could use some type of hydroxide. We could even use an amine like triethylamine. Some type of neutral nitrogen, sp3 amine. Etc. We could use bicarbonate, etc. Your choice of base, carboxylate. Then we come in with something like alpha iodide. What type of reaction can we get here? Good old SN2. And we didn't have an alpha more oxygen. So this is a different approach from the Fischer esterification. Here, this oxygen, well, actually we can't do that either because it could be either one. Because these oxygens are equivalent right here, right? Because in terms of resonance, if we draw the hybrid, isn't it really, I mean, either oxygen can end up with the alpha. They're equivalent at that point. So I can't really star this one and say it's that. But hopefully you see the approach. It's a good old-fashioned SN2 O-alkylation approach. So 2 different ways to make esters, yeah? C. Conversion to acid and hydrides. Conversion of what to acid and hydrides? Conversion of carboxylic acids to acid and hydrides. Reaction to carboxylate with an acid chloride. Okay, already I would have expected you to know this reaction outcome. All right? And that's another thing. As we move forward, you've got your general knowledge. You should be able to work this here and to show the product. You should be able to have predicted this already. Well, base is just going to make the anion, right? Nothing new. We throw in this, what type of reactivity are we going to have? Nucleophile. Very reactive here. Acid chlorides, reactive intermediates. Electrons come in here. What are we going to do? Electrons up. Phenyl. Oxygen came in here. Electrons up. Yeah? This was our nucleophile. Yeah? Added to carbon, electrons up. Tetrahedral intermediate, what's next? Electrons back down. We're going to kick off the chlorine. And what does that do? Gives that there, right? There you go. We just did a nucleophilic addition. Addition, elimination. Overall, it's an acyl substitution. Okay? Under my hand used to be chlorine. Now it's the oxygen and the rest. This is called a mixed anhydride. We'll cover anhydrides a little bit later. Anhydride again is oxygen bonded to 2 carbonyls. This is called mixed because the R groups coming off the carbonyls are not the same. We have a phenyl and a methyl. The term will make more sense when we introduce anhydrides. But the chemistry is pretty straightforward, right? It's just addition elimination. But what do? We were able to convert a carboxylic acid to an anhydride, or synthesize an anhydride from a carboxylic acid.
Dr. Stevens,
Uh-huh.
at the top of the page that you just flipped over from, I think last class we kind of just slides didn't really discuss what P-TSOH
Okay.
is.
All right, yeah. Let's go back up here. This is an exact example of a Fischer esterification. We talked about equilibrium. How do we drive this to the right?
More of the alcohol,
More alcohol.
like low boiling alcohol.
We don't really want to use more of that. That practically doesn't make much sense because you'll never get rid of that by using more of that. Well, this tends to be the main thing. If we want to go to the right, do we want to have any water around? If we add water, is it going to make it go that way? No, adding water is going to keep it from going that way. Now, we could use H2SO4, but that's an aqueous acid. Would you rather use an aqueous acid or a dry acid? Dry. Because water is going to hurt your equilibrium. Now, the reaction will work with sulfuric acid because you get just a little bit. It ain't much water. And you're going to have a lot of alcohol, and so it will be driven. But ideally it'd be best to use a dry acid. An example of a dry acid is para-toluene sulfonic acid. Okay? It's a dry acid. What is para-toluene sulfonic acid? Well, what's tosylate? Tosylate, right? Good leaving group. That's O-tos. Well, just put an H here, and that right there is the para is just added in here. It's para-toluene sulfonic acid. If under my hand was OH, that would be sulfuric acid. Well, that's an aqueous acid. But that is a dry acid. You can have this dry, or sulfuric acid can't be. Right? It's a sulfonic acid, a benzene sulfonic acid. Dry, actually also is solid. Where if you drop a bottle of sulfuric acid, you're going to have a mess. If you drop a bottle of this, you get the broom out and sweep it up. Okay? So it's practically a good choice of an acid. Good. Chemistry of acid chlorides. Also, some of this chemistry, this handout, will go back around and around and around. And, you know, we're like, did we just cover this? Yeah, we just did, but now we're under a different heading. Because now we're focusing on acid chloride. First off, how do you synthesize them? We synthesize them from carboxylic acids, and we've already done that. All right? So that we're already done there. How can you react them? Reaction with alcohols or waters to give water to give esters or acid. Acid chloride will react with water to give a carboxylic acid plus HCl. No catalyst required. You do not have to protonate this carbonyl to get it to react. Acid chloride is ready to react. Very reactive. All right? It's the most reactive of your carbonyl derivatives, acid derivatives. It will react with water. Basically, mechanism is what? Right? Nucleophilic addition. Electrons up. And what next?
The oxygen swings down and kicks off chlorine.
Back down. Which is a better leaving group, Cl or positive oxygen?
Cl. They're about the same.
To me, they're about the same. This comes back down. What if it comes back down and kicks off the water?
And you have what you started with.
Equilibrium.
This might just be an equilibrium, right? Do you think there's a chance it could come back down and kick off the chlorine?
Yes.
Right? If we want to go ahead, we could go this way, and when it kicks it off, what do we get? Reformed carbonyl, and you get the there plus Cl minus. And you can get home from there. I'll let you show the arrow there. Cl minus takes the H, right? do this with an alcohol. If there was an R group here, okay, one of these was an R group, the Cl minus is only going to take the H here, and you'll be left with the R group. If you're left with the R group, that would be an ester here. Okay? Acid chlorides react with water. Because of that, you're never going to find an acid chloride in nature. Because there's water in nature. All right? Unless it's some Sahara desert, I don't know, but there's water everywhere. Okay? Even in the desert. Acid chloride is never going to be a drug because as soon as you take it, it's just going to react and it will no longer be an acid chloride. It reacts with water. Acid chlorides are reactive intermediates that are used in the lab. Okay? For getting your carbonyl group on something. We're about out of time, is that right? Okay, guys. Have a good day.